Hello, so in this video I'm going to go over how to do a stability analysis in Ansys using a SOLIDWORKS model. So I'm going to pull up my fluid flow CFX file and right click over geometry and go to new design model or geometry. And this is going to take a few seconds to load. Then I'm going to go to File, Import External Geometry File, and select my file. So here I have my example one, where you can see a plane, and we want to export this as an IGS file, and we want to import it as an IGS. Then we generate it, and you can see it here. After that we go to Tools, then Enclosure, and generate that. And as you can see, there's a pretty large box around the plane structure, which is good. Then we want to go to Create Boolean and change the operation to subtract, target the box, and for the tool body select the solid that is the plane shape and apply it. Then generate that. Make sure to put preserve tool bodies on no, and we should end up with one part and one body. Now we're going to select faces and name our selections. So we're going to make this one the inlet, generate that. We're going to select the backside and the top sides as outlets for the airflow, because this is going to be a longitudinal, and that means alpha changing based analysis. We're going to apply the geometry and name it, generate that, and then selecting the sidewalls to be our fluid walls. So these are going to be free slip walls, and we want to double check that all of our boxes are covered. You can hold Control to select multiple faces at once, and then move around like this by holding down the scroll wheel. And finally, to select all the faces of our plane surface, we can go to right click, select all, and then holding Control we will deselect all the faces of the box. Then we can right click, go to name selection, apply, and call that plane surface, and generate that. Then I'm going to save this file. I'm going to call it glider stability test. And now I can close my geometry editor. Then I'm going to refresh my mesh. This will also take a few seconds. And once we see the lightning bolt appear, we can right click and edit. Click over the mesh and generate it. And we've successfully generated the mesh. So we're going to save that and exit out of the mesh editor. Then we want to right click over the mesh and update it. And now that we see it's done updating, we can double click on setup to edit that. In our setup tool, we want to create our boundary for the inlet, set the location to the inlet, and change the option to Cartesian velocity coordinates. So we want the main component of our velocity to be in negative z, so we're going to go to W and make it negative cosine, set it to equation, then do negative cosine of t divided by 50 seconds times 4. That's just our given example velocity, meters per second. And then we're going to copy this equation and put it in the v or y section and change it to negative sign so the flow comes down onto our plane. So I've edited the time to be t over 25 seconds just to make it run faster, and set the u velocity to 0. So I'm going to OK that, and then add another boundary for fluid walls. Boundary type to wall, make it a free slip wall, and OK that. And then I'll create the outlet, and change the average static pressure to 0. Then I'm going to create a plane surface. It will be a wall, and we will make it a no-slip wall with a roughness of 0.25 millimeters. Make sure to change the units, and OK that. Defining this surface is very important for expressions we are about to create. But first we're going to change our analysis type to transient, set the total time to 80, set the time steps to 1 second, and the initial time as 0. And here you can see the errors pop up, so we need to edit our domain, default domain, which is this here, and give it an initialization. So since the flow starts off, we want it to be what our time would be, the values for velocity would be at t equals 0. So that's 0, 0, and negative 4 meters per second, and a static pressure of 0. So we're going to apply that, and you can see the warning went away. And then we need to go to flow analysis number 1's output control and give it transient results file. So we're just going to give it the default name and give the time step interval of 1 second for simplicity. Now we're going to go to our expressions. We're going to name the first one lift. So I've covered how to create expressions before, but they will change each time. So this one is going to be the force in the z direction times -1. Then we have parentheses and do at plane surface, which is going to be equal to whatever the name of your defined plane surface is. Then we create a new expression called drag. Oh, sorry, I made an error on that previous one. This should be force in y with no negative sign. So we're going to copy that expression, then create our drag expression. So this one is the negative force of z on the plane surface. Then we're going to create another expression called moment. So that one's going to be moment around the x direction at the plane surface. However, this would be not quite aligning with the typical way I do in an XFLR, so I'm going to add a negative sign to keep typical expressions correct. Then we want to add a coefficient of moment, which is going to be equal to moment, but multiplied by a factor. So we're going to go to expressions, call it CM, both capitalized, and go define it as moment divided by 0.5 times 1.225, which is the typical density of air, times 16, which is the velocity we're going with squared, times the area of the wings. And so we can go to our SolidWorks file, evaluate that, we measure these here, and we want units in meters. And we want a bit more precision, so we're going to go to 4 decimal places. And so that's 0.032, roughly, meters squared. So 0.064 is a good area approximation. And then we want a mean aerodynamic chord, which is the length of this chord here. And so it's 0.0924 meters. I'll post the equation now. And now we have all our expressions defined. And since we have no warnings, we can save and move on to the next step. So we'll double click on solution. And start run. And our solution completed normally, so we can exit out of that and load our results. So since we're primarily interested in the coefficient of moment, we're going to create a text that can show us what the value was. We're just going to call the text CM text, and embedded auto annotation, and change the expression to CM. So now we have our expression for the coefficient of moment. And if we go back to our SolidWorks file, we can see that the origin starts here. So very much right here at the front of our fuselage, which is this far back from where our wings are located. We can change the location of this by changing the X justification to left and applying it. And for the moment that looks fairly good, so we'll leave it there. We also want to load in our expression for lift. So we'll create another text for it. And change the expression to lift, apply it, change that. Change the location to a left justification, and the Y we will move down, and so it's there. Then we can also bring in drag. Embed auto annotation, set it to drag, and apply it. Change location, and apply that change. And we also want to see the time step at each position, so we need another text piece. And just call that time, and apply it. You can also use this manual slider as you wish, and change the X justification to left. And this time is in seconds, remember? Actually, we gotta make sure it's on current time step. So now if we were to go and animate it from time step 0, we can see how the values change over time. We can also add in the streamlines to visually verify how the flow works. We're going to increase the number of points and apply it. So this is what it looks like at time step 80, which we had it set to. We're going to change the range to local, and so that gives us a much more clear idea of how the velocity changes. However, we probably want to remove the this part here, as it blocks a lot of our text. So actually we're just going to make it invisible for now. Oh, and we just saw our coefficient of moment pass into the negative range. So we're going to stop it and scroll back a bit. And going by single time steps, we can see it occurs sometime between time step 36 and 37. Now, keep in mind that this representation, however, does not have any mass, so that would also be an important effect on moments. So we're going to load all of this data into a table now. Here you can see my tables I've used to calculate the various aspects of stability. So I start with the time values, from which I can then derive the velocities and the angle of attack for the plane in the simulation. I inputted the lift, drag, and moment about the origin values, and was able to calculate the x center of pressure and the moment about that center of gravity. Using the COG, I also recorded the area, velocity, rho, mean aerodynamic chord, mass, and the x location of the wings, which can be deduced from my SOLIDWORKS file. So if I go to this line segment here, the wings start 1.332 meters away from the origin. I can also calculate the glide ratio and the change in angle of attack. And from this I can deduce the moment about the front of the wings using a moment equation, which I can then turn into the coefficient of moment and coefficient of moment slope, which multiplied by 180 over pi gives me the static margin. Now, Due to the simulation's imperfections, we want to average all of these out to get a rough approximation of the average slope, which is negative 0.414 in this case, and this static margin value seems to be a lot larger and positive compared to its neighbors. So if this one were 0, for example, the static margin goes up to negative 0.86, which is in that negative 1/2 to negative 1.5 range that we want it to be. So we may have a stable glider configuration, assuming the center of gravity is at this location and has this amount of mass. This table should be publicly available through my Discord link, which will redirect you to the Ansys sub-Discord section, and then link to the Google Drive file in which I have this.